get to pay homage to the demo gods.
Takes a while to run, so I only get one shot.
Right.
All right, thanks for joining me, everybody. Hope everybody can hear me. My name is Spencer McIntyre. I'm very excited to be speaking here at BSides Cleveland again, and I'm going to be talking to you about automating some Windows kernel analysis utilizing symbolic execution. So we're going to talk about what that is and go over how we can actually utilize symbolic execution and do a bit of a showcase on like how we can actually use it to automate some analysis for kernel mode code, in particular a driver, which is what we're going to take a look at. So this is what we're going to go over pretty quick. We're going to do a real quick intro, and then we're going to talk about what symbolic execution is. It's a bit of a newer technique, and there's like a ton of like research out there on it. And in like my opinion, my general misinformed observations perhaps are that over the past like couple of years, it's started to definitely come out of the realm of academic research and into actual like practical use cases. So it's something that is definitely starting to pick up, and just my own personal ideas I'm thinking is going to continue to take off as people are using it more and more to do automated analysis of like low level like binary code. Hopefully after this you'll understand what it is and see like an example of like how it actually can be used and makes things way easier. So we're going to talk about kernel execution, then we're going to talk about the kernel environment notes. So we can go over briefly like what the kernel environment is, how it's different from userland, and particularly in how this relates to our symbolic execution utilizing Anger. Then we're going to wrap up with our case study and do some closing thoughts, which I kind of already gave away some closing thoughts, so I'll try to kick that off. We're going to kick off the demo now, though. So we're going to do this a little bit out of order, and that's because the demo takes a few minutes to run, and so we don't just want to sit here at the very end and like watch it not do anything. So I'm going to kick it off now, and then we're going to go over what it's doing, and then at the very end we're going to take a look through the results, and hopefully it works, because it does take a few minutes. You only get one shot at this. So let's stand by here. Okay, so we have kicked off the demo code, and this particular sample is going after a driver that I had hand selected. It's a very small driver, so on my system, which isn't quite as powerful as like my beefy work laptop, it takes about somewhere between 45 seconds to a minute and a half to run. But we're going to come back to that, and we're going to take a look at what the results were. Even with this was like a smaller driver, so the analysis is actually much faster than other times. Sometimes I got to like start it up, go watch a movie or something like that, and then come back. But, alright, so what are we actually doing right now? So now we're actually, in the background, what we can't see is that this driver is being analyzed utilizing symbolic execution to pull out a few pieces of information that we're looking for. But what is symbolic execution? So I'd mentioned that this is sort of a new-ish technology. It started coming out really around a couple of years ago with the DARPA Cyber Grand Challenge. There were like symbolic execution frameworks that were coming out of that were starting to be publicly released. One of the largest and most well-known ones is the Anger framework, which is what we're going to talk about using today. Still under active development. They're making a lot of new features on it, so it's a really fascinating project, and the team around it is fantastic. They're really helpful, they're really smart people, and they're really welcoming and inclusive to new users to it. So I highly recommend you talk to them. They're very helpful in that regards. So what would we utilize symbolic execution for? So it's used to quote unquote explore binaries. They have like an entire section in their documentation on like exploring binaries. What we're looking here to do is like obtain maximum coverage. So if you're gonna not use symbolic execution, you're gonna use like emulation or something like that. Every time you execute the binary, you're gonna have exactly like one flow path. You're only ever gonna have like one point where like, the instruction pointer is this, then it's that, then like, maybe depending on variable, it either takes one branch or another, but it never takes both, and it just continues on linearly, and that's how the execution just works. Symbolic execution is a little bit different. We'll have a graphic that's going to display that, but is built on top of this thing called satisfiable modulo theories, or an SMT solver. One of the most popular ones is going to be Microsoft Z3. This is also an open source project. It's a cross-platform SMT solver that's one of the core components of Anger that basically allows it to say like all of the mathematical constraints, like if x needs to be greater than or equal to 2 and needs to be less than 5, that is satisfiable. We know that the values 3 and 4, and I think I said greater than or equal to 2, 2, 2, 3, and 4 would all satisfy that constraint, and Z3 allows you to take all of those constraints and determine whether or not that's ever going to be possible. How this translates to our binaries, we know, like, if these are our constraints to go down this particular path that we're interested in, can we ever actually do it? And so, I mean, presumably if the code exists under some type of constraints, that might happen, but when that comes interesting for us from an exploitation point of view is we can say we control this value, and we can only ever set it to 5 due to, like, outside things. You know, maybe in order to get to this point, it only ever has to be 5. And so we would want to say, like, given that this is 5, what other constraints do we have? Is it possible to go down this other code path that we are actually interested in? That's kind of where the SMT solver comes in. So we talked about sort of like a linear, or what they refer to as like canonical execution. That's what we typically think of. That's what your CPU does when you're like executing, or if you're using like emulation or something. What symbolic execution does is when symbolic execution reaches a branch, we're taking this example over here called x is greater than 3. It's going to split out, and it's going to have 2 different states at this point, and it's going to keep track of both of them at this point. On the left-hand side, we have state equals 1. So you can say that x was greater than 3, and because x was greater than 3, it's going to execute function 1. In this case, function 2 was not executed from this state, because x cannot be both greater than 3 and at the same time less than or equal to 3. That doesn't make sense. That can't happen. So it's only going to be one or the other. However, on the flip side, we're also going to have a second state, in which case this evaluation was the alternative, and we have x is not x greater than 3. So I put not x is greater than 3 because if you actually look at how it does it internally, that's how it is, and you need something to simplify that to say x is less than or equal to 3. That's more of like a human construct, and that would involve actually simplifying that mathematical formula. Just internally, it's just not x is greater than 3. But in that case, we're going to come down here, we're going to execute function 2. So when we reach this branch, the symbolic execution is actually going to create 2 new outputs for us, so that way we can track it on both sides, and it's going to then track the constraints. So if we were interested in function 1, we could tell that we can only ever reach there when x is greater than 3. Presumably with a very large program, or not even a very large program, a very small program, if you want to say, I want to reach this function, how would I get here? You're going to be able to inspect the state, and you're going to be able to track or take a look at all of the constraints that Anger has tracked for you. You're going to have this long list of them. You're going to say, x needs to be greater than 3, y needs to be less than 15, all of these other types of things, and you'll be able to apply context to them to say, well, x came from the result of this other function over here, so I know this other function over here needs to return this, and hopefully that will help you identify if you want to go to function 1 that's how you would get there. So, okay, so symbolic execution. So Anger is an open source framework that does this. It's implemented mostly in Python. There are some C components but for the most part, it's implemented in Python. They've actually recently moved it from Python 2 to Python 3 in one of the later versions. So that's really nice. So they're keeping it up in like the more modern versions. One of the notable exceptions of components that are not actually implemented in Python is going to be libvex. This is one of the core parts of Anger. Another one of the core parts that really is where like the secret sauce is that allows Anger to support multiple different architectures. If you look at the architectures that Anger supports, it's a very impressive set. You might be thinking, wow, like they implemented all of these architectures. Libvex is the secret sauce that allows them to do that. And what that does is that lifts the instructions into an intermediary representation. So they only ever have to handle the intermediary representation. They first take the input, pass it over to libvex, and they just process that intermediary representation with their own internal implementation that's going to go through and actually calculate, like, okay, for example, if you're like pushing EAX onto the stack, you know that the value of EAX is going to be read, and then the stack pointer is going to be referenced, and they're going to be writing to the stack pointer, and then they're going to be changing the value of the stack pointer. So that's all just like one assembly instruction for like push EAX, but that intermediary representation is going to lift that into those smaller steps, and that's the level that their simulation engine operates on. So that's how they are able to support so many different architectures. So in addition to Anger, there's also some other additional components. They have CLE, which is one of those self-referencing acronyms that CLE loads everything. It's their like binary loader, so you can pass it in like an ELF file, a PE executable, which is what we're going to be doing, and it's going to handle mapping out all of the different locations in memory so that it actually knows what the memory layout would look like at the time of simulation where it's going through those. And then Clarity is a convenient abstraction over like the SMT solver, so utilizing all your variables that you then pass down into Z3 that you're utilizing for your constraints. Clarity like handles some of that abstraction, makes it a lot easier in order to work with it programmatically. Okay. So SimOS is one of the core components of Anger that it actually does include itself. This is what actually represents the simulation for the operating system. So Anger provides one for Windows and one for Linux. So what we're going to be talking about mostly is going to be the one for the Windows environment. So all those intrinsics, those things that you know that are individual to Windows, such as like how errors are handled, how DLLs are loaded, things along those lines, the general memory layout, that's going to be implemented by this class right here. If you wanted to add in your own operating systems to be supported by Anger, this is sort of like where you would start to update. One of the first challenges I had when I was setting out to do some of this analysis was that driver mode PE objects have the GS stack cookie enabled, and the loader needs to be able to initialize that value, lest when you go to actually like execute your main method in your driver, it always fails out saying that the stack cookie is invalid, because in the driver mode, that's expected to be initialized by the operating system. So in this case, that operating system would have been simulated by Anger's SimOS class, which wasn't initializing that value, was effectively causing all drivers to not load and fail. So you can actually specify how you want those stack cookies to be done in Anger with some of the newer versions. Okay, so with the differences between like user mode and like kernel mode code, one of the bigger things is going to be like addresses are going to be much higher. So in 32-bit, you're going to have 80 followed by, was that like 6 zeros? On kernel, or on 64-bit, you're going to have 5 Fs, 8, 0, 0, and then like in WinBag notation, you have like that backtick. The addresses are always going to be higher because that's where your code just exists. That's how the operating system's laid out. It's similar on Linux. The higher addresses, that top half of the address space is always reserved for the operating system. That's just how they work. So one of the things that when you load code, any type of code, whether it's user mode or kernel mode into Anger, it's going to set up a lot of environments for you. So what you need to keep in mind, though, is that Anger, as it is right now, is a little bit more geared towards, not a little bit, is basically, from what I've seen, completely geared towards emulating user mode code. So it does some changes on some of those like lower level address locations, where it'll set up some hooks for some common functionalities from like kernel 32, NTDLL, and it'll set up some of that environment for you, so that way the code that you're emulating has that functionality available to it, and you hopefully have a much more smooth simulation experience. Okay, beyond that, there are some binary specifics to some of these different types of code. Some of the instructions are actually privileged instructions. Now, you would never run into these on like when you're emulating like user mode code, because if you did, they would crash. Specifically, if you have like the manufacturer specific registers, or the MSRs, there's like an RD MSR and a WR MSR calls to read and write to these manufacturer specific registers. These are privileged instructions that are only intended to be executed by kernel mode code. If you run these as like a user mode, you're going to have an access violation. You're going to have issues because it's going to say like you can't do that. This is reserved for privileged code. Drivers will sometimes do this because they have the need to pull out some of these manufacturer specific things if they're looking at like hopefully they're not looking at the syscall, but the internal operating system of course would use this, like set up the syscall dispatcher and things along those lines. So the MSR instructions, the read and write to those, and int29, which is going to raise a security check failure, those are two very common instructions that, or excuse me, 3 common instructions that are utilized by drivers that Anger is just not equipped to handle, because a lot of the infrastructure, once again, is geared much more towards user mode code. So what you can actually do is Anger provides a specification in order to be able to actually implement your own instructions within Python and emulate what would happen while operating on that intermediary representation provided by libvex. So you can actually say, you can extend Anger's functionality and say, I know what this instruction is, don't worry about it, make these changes, do these things to the registers, and carry on. So if you're dealing with driver mode code and you don't have that code coverage, that's the type of thing that you'll need to implement. And there will be examples of that in the code that I'll release at the very end that we're running in the background that hopefully hasn't crashed yet. Not yet. I mean, it's totally not going to crash. All right, so driver objects. So of course we're talking about kernel mode code. In this context, though, like we're not really talking about the kernel itself. We want to talk about drivers more specifically, because that's what I'm more used to worrying about. And so when I set out to do a lot of this, it was because I was working on projects in order to fuzz drivers over the device I/O control routine, which is a very useful attack vector. You can immediately get data in and out of the driver, so it's an interesting attack vector. However, if you hypothetically have a fuzzer to target that, you need to know some information about your drivers. If you're just given a driver and you say, like, is this going to be a good candidate for this type of a fuzzing, you need to know a few pieces of information before you can answer that question. One of those pieces of information is, does this even provide that interface? And if it does, what are the IOCTLs that we can feed it that will actually cause it to do something? Because most of the IOCTLs aren't going to be handled by the driver and just not going to do anything. So you'll end up wasting time cycles by fuzzing these entries that just don't exist. In addition to the IOCTLs, we want to know if there are any constraints on the input and the output buffers. A lot of times drivers will say, you know, IOCTL like 27 requires that the input length is always exactly 20 bytes. So if you're lucky enough to randomly hit IOCTL 27, but you're passing it 19 or 21 bytes, you're still not going to get maximum code coverage, so you're not going to be able to identify vulnerabilities because you're just not hitting it. Okay, but so that was sort of what we were trying out for, and that's what we're looking for in drivers. But driver objects themselves are PE files, just like executables and DLLs, like at the file system level, the way the file itself is actually laid out. Of course, it's much different in how it's loaded and things like that, but the actual file format as it exists on disk is just another PE file. The entry point is unique. Executables, DLLs, and driver files, sys files, they're all PE files, but they all have entry points that will get executed upon loading. But the entry points are different. They have a different signature, so they're called with different arguments, effectively. So for drivers have this driver initialize function, and they're passed in these two variables, those two values. So the driver object is going to be the one that we're going to be more interested in because drivers extensively utilize callbacks. Basically, when a driver is loaded, one of the most common things it's going to do is in its driver initialize routine, it's going to register a whole bunch of callbacks to do all the functionality that it needs to do. Handle devices that are plugged in, handle IOCTL, it's going to register devices, maybe like it's a firewall filter or something like that. It's going to work with the firewall subsystem, but it's going to install all of these callbacks, and then it's going to return back. So that's one of the first things that we need to do. If we don't want to like manually analyze this function, which like I've done, it's awful, it takes forever. That's what we want to utilize symbolic execution for. So we want to pass it a symbolically implemented driver object, and we basically want to run it through the driver initialize function and see what changes, what callbacks are you installing on it, where does this value go, how are you using it, so we can get some context as to what this driver is actually doing. So in order to do that, like I'd mentioned, we are going to execute that driver initialize code. So when we do that and we want to simulate this, Anger provides a couple of different states that we can start out with just for convenience. These are all done through the factory function. So we have an entry state, which is going to be useful for emulating like the entry point of an executable. We can't use this at all because that's going to be for like normal user mode binary. So that one's right out. Then there's like the blank state, which would set up basically just all the internal information for Anger. It's actually the one that call state and entry state use on the back end, but the blank state, as the name implies, is not going to have any information for us. The one that we actually want to utilize is going to be the call state, which is basically setting up a state that's going to emulate like a call instruction, which is effectively what we're doing. We are emulating a call to that driver initialize routine, so we're going to go ahead and we're going to use that one, and then we're just going to fix up a couple of the values that it needs. At this point, we would need to know things like the calling convention. So on 64-bit, we need to know that like our first argument is going to be that RCX register, with the second argument that RDX register. So because we know that, it's documented by Microsoft, we can update the call state in order to emulate that information. After that, we need to know the driver object, the layout. This is also going to be documented. I'm going to skip ahead a little bit because I'm sort of running on time and I want to show the output. But the structure is going to have all of this, so we would have this information from the driver object. And what we're going to do is we're going to back this object in memory with different symbolic objects provided by Anger at the different locations of where it would be laid out. So if this object, and don't quote me on this because I don't remember the specific, if this were 100 bytes with the first 4 bytes being a D word or something like that, we would determine where we wanted this object to exist within the memory that was created for us by our state, and we created a symbolic object, a unsigned integer 32, and we placed it at that first address, and we would continue with this pattern setting up our driver object and allowing us to break it out by the individual fields. That way we can reference these later on and see how these are actually being utilized. So it's quite tedious in order to set up a structure object in the memory of the state, but it's much more beneficial because you have easier analysis time after you've run through, so you can tell what individual members of the structure were actually being used for and what their constraints are, and if they were updated, what those values were. So once we actually have that, we can do things like trace for IOCTLs because these are dispatched through structures. So like I had mentioned, we want to know what the IOCTL value itself actually is in addition to the input buffer, the output buffer. So those are going to be pointers to locations in memory as well as their lengths. So the length would be an input value that we, the attacker, or the user, or whoever, would be providing into the driver. So we'll keep that a reference to that so we can see what the constraints are on that. However, the IOCTL, we want to also be able to track that in addition so we know which values we can actually incorporate. Once we've used this to actually identify where the routine is, we can tell, if we know what the function is, we can simulate this out, and then we can filter out all the states that we can tell were errored out. We can basically see if there was an error condition, we can get rid of all of those states because we know it didn't actually execute all the code that we were interested in, and then we can process in batch all of the states that were collected that didn't result in error condition, presumably were successful, and we can see what the constraints are on there. And what that'll do is that'll allow us to list out that those constraints included the IOCTL for this particular state of, like 1 of 50 or something like that, was this value. And in addition to that, the input control code was, less than 16, and the output was greater than like 200. So you had at least 200 bytes allocated for the output. So we would collect all of these states, which is happening right now, and then we'd be able to go through and validate the constraints on those, and that gives us the information that we would need to go in into our fuzzer, and we know that we can increase the code coverage. From that point, we can start to communicate with the driver in an automated fashion. Okay. So let's go ahead and see what happened from the driver. And there we go. Okay, so what this was doing was running in the background. So the top up here, it's printing out some basic information. We're pulling out the device name, which is just like a string that we're pulling out of the output file. Basically just running strings on it, and we know that that is the device handle that we would load in order to actually communicate with it. After that is where the symbolic execution actually begins, and then so we can tell that we have all of these IOCTL codes. Just before that, it's going to have identified with an offset the control routine. So where the location that I got that information from was that it identified the driver initialize function just by simply reading the PE header. It set up our structure in memory, and then it executed that to determine what was being set on that driver object, how it was being utilized, and it looked at that from a contextual perspective. It then knows that at that particular offset is the function that's being used as the control routine for the device that was registered up here. So after that, we then have a table of all the different IOCTLs and the different constraints for the states that we have effectively filtered out, as these were not errored states. And I say that very specifically, that these do not result in an error condition, which is why you can see multiple states have the same IOCTL. If you take a look at this one up here, this one's duplicated multiple times. So these were all individual states, and each time they actually had the same input length, but the output was sometimes different. So if you wanted to interface with this driver utilizing this IOCTL, your input buffer length is going to need to be less than or, greater than or equal to 0x18. So that be 24 bytes, and the output buffer length needs to be greater than or equal to 8. So now you know that information. You didn't have to load it up in like a disassembler and like walk through it. When I was doing this manually, this would take hours, if not a day or two. I mean, maybe I'm not the greatest reverse engineer, but having it done in like a couple of minutes has saved massive amounts of time, and is helping with the triaging of taking these drivers and determining whether or not they present a viable attack surface for further investigation. Okay, and with that, thanks everyone. The code that was actually the driver analysis is up. It is public right now. It is on GitHub. It's not documented, but it is public right now. You can pull that down using Anger. I plan on working on it a little bit more. I started it quite a few months ago, right around the same time that Anger switched over to using Python 3, so it's still all implemented in Python 2. But you can utilize this to basically tell the attack surface of a particular driver. So, does anybody have any questions? Sorry, I know I went a little bit quick because that was a lot of information to get through. So, all right. Well, thank you very much, everyone.